All right. Welcome back, everyone, for another deep dive. You know how this works. We take a complex topic, something you hear about all the time but maybe don't fully understand, and we break it down.
Exactly.
So today, we're diving into the world of optimization algorithms.
Ooh, exciting stuff.
I know, right? They're kind of the unsung heroes of machine learning. I mean, think about it, you hear about AI and machine learning all the time these
All
days.
the time. Yep.
But behind all that impressive stuff that AI can do.
Self-driving cars, beating chess champions.
Right, exactly. Behind all of it are these algorithms, these optimization algorithms, working tirelessly behind the scenes.
It's true. They don't get the spotlight, but they're the ones that make the magic happen.
So let's demystify them, shall we? Let's answer the question. What are optimization algorithms and why should we care?
Okay, so at the most basic level, an optimization algorithm is like a set of instructions for a computer program.
Okay, instructions. Makes sense.
And these instructions, what they do is they tell the program how to adjust and tweak a machine learning model to make it better.
So to make it more accurate, I guess.
Precisely. More accurate, more efficient, better at whatever task it's supposed to be doing.
I see. So it's like training a dog. Kind of. You give it instructions and rewards to shape its behavior.
Yeah, that's a good analogy. But instead of treats, we use data. And instead of a dog, we have a complex mathematical model.
Right, of course. Data, not treats. So walk me through how this actually works in practice. What are these algorithms doing with the data?
Okay. Imagine you're trying to train a model to predict housing prices, right?
Yeah, that's a classic example.
So you feed it a ton of data about houses. Square footage, location, number of bedrooms, you name it.
And the goal is for the model to learn from this data, right? To figure out how all these factors affect the price.
Exactly. But here's the thing. The model starts out pretty clueless. It doesn't know which factors are important or how they relate to the final price.
So it needs a guide, a coach, to point it in the right direction.
That's where optimization algorithms come in. They're like the coach, the personal trainer for the model. They look at the data and the model's predictions and say, hey, you're a little off here, tweak this a bit, adjust that a bit.
So they're constantly refining, constantly improving the model based on the data.
Exactly. It's an iterative process. The algorithm looks at the data, evaluates the model's performance, makes adjustments, and repeats.
Fascinating. So these algorithms are really the engine behind machine learning, making sure those models actually learn and get smarter over time.
They are. They're the key to unlocking the potential of AI, making sure it delivers on its promises.
But how do these algorithms actually do this? I mean, what's going on under the hood?
Well, that's where things get a little more technical. We're talking about mathematical concepts like gradients, objective functions, learning rates.
Sounds complicated.
It can be, but let's try to break it down. Imagine you're a hiker trying to find the lowest point in a valley.
Okay, I'm picturing it. Beautiful scenery.
Now, the landscape you're navigating represents all the possible combinations of parameters in your model.
Parameters.
Yeah.
Like the settings, the knobs, and dials of the model.
Exactly. And the lowest point in the valley, that represents the optimal set of parameters, the ones that make the model perform the best.
I see. So the algorithm is like the hiker, trying to find the best path down to the bottom of the valley.
Precisely. And the way it finds its way is by following the slope of the landscape. That slope, mathematically speaking, is the gradient.
So the gradient tells the algorithm which way to go, which direction leads to better performance.
Exactly. The algorithm takes small steps downhill, following the negative gradient, always seeking a lower point, a better score.
It's amazing how such a simple concept can power such complex processes.
It really is, and there are different ways to follow that gradient, different strategies for navigating the landscape. That's where the different types of optimization algorithms come in.
Okay, so let's talk about some of the different types.
Sure. One of the most basic algorithms is called gradient descent.
Gradient descent? That sounds familiar.
It's the classic, the foundation of many other algorithms. It's like our hiker taking small, careful steps downhill, always checking the slope before taking the next step.
Very methodical, very cautious.
Exactly, but it can be a bit slow, especially if the landscape is vast and complex.
So what if we want to speed things up a bit?
Well, that's where stochastic gradient descent comes in, or SGD for short.
SGD, okay. What's the trick with this one?
It's like giving our hiker a pair of running shoes. Instead of using all the data to calculate the gradient, SGD uses only a small, random sample.
So it's taking bigger, faster steps, but maybe not always in the exact right direction.
That's the trade-off. It sacrifices a bit of precision for speed, but it can be much more efficient for large data sets.
I can see how that would be useful when you're dealing with millions or even billions of data points.
Absolutely. And then there's momentum, which is another way to speed up gradient descent.
Momentum, like the hikers building up speed as they go downhill.
Exactly. It remembers the direction of previous steps and uses that information to accelerate the descent.
So it's not just reacting to the current slope, but also considering its past trajectory.
That's right. It helps avoid getting stuck in small valleys or bouncing around aimlessly.
Clever.
Hmm.
And then you mentioned Adam earlier. That one sounds almost human.
Right. Adam is like giving our hiker a map and a compass, plus those high-tech running shoes we talked about.
So it's combining the best of all worlds.
In a way, yes. It combines momentum with an adaptive learning rate, meaning it can adjust the size of its steps based on the terrain.
It sounds like Adam is a real all-star in the optimization world.
It's definitely a popular and powerful algorithm, but there's a whole other class of algorithms we haven't even touched on yet, second-order methods.
Second order. Okay. What makes them different?
They go beyond just looking at the slope, the gradient.
Yeah.
They also consider the curvature of the landscape.
Curvature, huh? That sounds a bit more abstract.
It is, but think of it this way. Knowing the curvature can help you take more direct routes to the lowest point. Imagine our hiker can now see the entire valley and plan the most efficient path down.
So second order methods are like taking a shortcut, a more informed approach.
Exactly. One example is Newton's method, but it can be computationally expensive.
So there are trade-offs here too, just like with first order methods.
Always trade-offs. Faster convergence might come at the cost of more complex calculations.
I'm starting to see a pattern here. So ultimately, choosing the right optimization algorithm depends on the specific problem you're trying to solve.
Absolutely. It's like choosing the right tool for the job.
Yeah.
You wouldn't use a hammer to screw in a light bulb, would you?
Hopefully not. So what are some of the key factors to consider when making this choice?
Well, one is the size of your data set. For massive data sets, SGD might be your best bet, but for smaller data sets, gradient descent or Atom might be better choices.
Okay, data set size, got it. What else?
The complexity of your model is another key factor. More complex models with lots of parameters might benefit from more advanced algorithms like Atom or even second-order methods.
So it's about finding the right balance between speed, accuracy, and computational resources.
That's the name of the game. And it's an active area of research. People are always coming up with new and improved algorithms.
It's amazing to think about all the work that goes into making these algorithms, all the brilliant minds pushing the boundaries of what's possible.
It really is. And it's all in service of making AI better, more powerful, more capable of solving real-world problems.
And sometimes we don't even realize it's happening, right? We just see the end result, the cool AI application, and don't think about the optimization algorithms working tirelessly behind the scenes.
Right. They're the silent partners in the AI revolution, making sure the whole system runs smoothly.
Well, I think we've done a pretty good job of shining a light on these unsung heroes today.
I agree. We've gone from the basics of what optimization algorithms are to some of the more advanced concepts.
And hopefully our listeners now have a better understanding of how these algorithms shape the AI landscape and drive innovation.
Absolutely. But this is just the beginning. There's so much more to explore in the world of optimization.
And that's the beauty of it all, right? The constant learning, the continuous exploration.
Exactly. So to our listeners, I encourage you to keep digging, keep learning, and who knows, maybe you'll be the one to discover the next breakthrough in optimization algorithms.
Maybe one of our listeners will be the one to create an algorithm so efficient it solves all the world's problems.
Oh, that would be something.
All right, on that hopeful note, we'll wrap up this deep dive. Thanks for joining us.
Thanks for having me. It was a pleasure diving deep into the world of optimization algorithms.
And to our listeners, until next time, keep exploring, keep questioning, and keep learning.